So to monitor quantum network performance, we first need to be constantly tracking and monitoring these metrics, which means we kind of always need to be estimating the metrics in some capacity. However, we must be careful because if we spend too much effort on monitoring our metrics, this will take away from our ability to actually perform networking services on the quantum network. Once we have these monitored and tracked metrics, we can then analyze the metrics to gain insights about the quantum network performance. This might tell us about the quality of the protocols that we're running on the network. This can tell us about the cost of the protocols that we're running and the value that we're getting out of the services on the network. And it can tell us if there's bottlenecks in the performance of the network, things that might need to be addressed. After the metrics have been analyzed, of course, we can go back and optimize the metrics, where essentially we can fine-tune the network to try to improve things like fidelity, efficiency, and rates of the quantum network. Once we have the metrics, it's easy to optimize them and see the changes in real time or over time. Now, an example of tracking metrics over time is given by this paper from Brookhaven National Lab and Stony Brook University. Here, what they did is they measured the qubit transition between Brookhaven National Lab and Stony Brook University, which is about 50 kilometers of transmission over optical fiber cable. Now, these polarization qubits were sent across this optical fiber. A polarization state was encoded at one end, and the state was measured at another end, where they tracked the fidelity, which is essentially how close is my output state to the one that was put into the fiber. To do this, there were 3 different measurements that need to be performed, which are these Stokes parameters, which are the 3 bars at the top of this graph. So this S1, S2, and S3 are different expectations or different the expectations of measurements in different bases X, Y, and Z. This measurement data is combined to estimate the fidelity, and this fidelity is pretty much tracked throughout the span of about 10 hours here. And every 15 minutes within this 10-hour span, they perform polarization compensation, which basically corrects for all the noise in the fiber, realigning the input state with the output state such that there's a high fidelity transmission. So every 15 minutes, they correct the fiber for high fidelity transmission. And over that next 15-minute spans, the fiber starts to be affected by environmental noise and the fidelity decreases. Now, what you can see, for instance, in this blue region between 10 p.m. and midnight, there's relatively high fidelity throughout the entire time region. And the reason for this is that this is in the middle of the night. There isn't a lot of auto traffic on the road that is along the deployed fibers. The fibers are buried in the ground right alongside a highway. Now, in the morning, when lots of cars and trucks and trains start driving down these roads, we can see that there is a lot of noise between 5 and 7 a.m., and this is all attributed to the vibrations caused by the nearby auto traffic that is on the highway. Now, as we have vibrations, this causes the fiber to vibrate, which causes the polarizations in the fiber to have some changes on them, which causes the fidelity to decrease. And this can all be seen by monitoring this fiber over time. However, we should be careful to note that this data that we see here is constant monitoring of the fidelity over time. So there are no services being rendered on this network. There's only the measurement and estimation of fidelity over a 10-hour period.